So I'm very pleased to introduce David Chiang for the first speaker of this semester. David is a research assistant professor at the University of Southern California and the Information Sciences Institute. He got his PhD from the University of Pennsylvania and did a postdoc just down the road at the University of Maryland. His 2005 ACL paper won the Best Paper Award and really inspired a lot of interest in synchronous context-free grammar models for statistical machine translation. And we ourselves have adopted this formalism in our own internal projects for SMT. So I hope that he'll tell us what the next great thing is going to be.
And you should preface this with the fact that we heard his ACL 2005 talk before ACL 2005 because he gave it here. So you might just be witnessing the next best paper.
Fingers crossed.
Okay, thank you. So this talk is called Online Large Margin Training of Syntactic and Structural Features, and this is a paper that will appear at EMNLP.
Is it the next large thing?
Is it the next large thing? Yeah, large margin thing. Yeah, and it's available online, actually, as of yesterday. And this is joint work with Yuval Martin and Philip Resnick at Maryland. Okay, so what is this talk about? Here's the one-slide summary. Zhifei Li asked me earlier today to share about what are the things that I dislike about Hyro, which is this machine translation system that Chris mentioned. And so I promised that I would devote the first part of the talk talking about what I don't like about Hyro and how I would like to improve it. And so these are two classes of features that would be nice to add to Hyro. One is the soft syntactic constraints of Martin and Resnick, which they presented at this year's ACL. And another is a set of distortion features that are kind of sort of inspired by the distortion model of a phrase-based machine translation system, but adapted for a grammatical system. And I'll explain more what that means in a bit. And then the second part of the talk is really the meat of the talk, which is how to properly train these features, because it turns out that you don't really get the full benefit out of them using the standard training method, minimum error rate training. And so building on work by Watanabe et al. From last year's EMNLP, I'm using a method called Mira, which was introduced by Kobe Kramer, and making a couple of improvements. And the bottom line is that we're able to improve translation quality quite a bit using these new features. So these blue scores are on the NIST 2006 data, Newswire news groups only.
Is there a subjective improvement also?
Is there subjective improvement also? I'll have to get back to you on that. Yeah.
If you don't believe that you will
Let's not get into that already.
Sometimes, I would guess actually that the subjective improvements might be greater than what really is.
Yeah, I have to take a look at it. I've not had the chance to examine them too much. Yeah. Okay. So this is just a really brief overview of how the basic translation model works. This is a sentence some of you have seen before. I will use this thing. It says, Australia is with North Korea has diplomatic relations. This word is untranslatable. Few countries, one of. Okay, did that make sense to you? No, right? I'll say it again. Australia is with North Korea has diplomatic relations, untranslatable, few countries, one of. Okay, so this is an example of a Chinese sentence where you have to do quite a lot of reordering to get to the proper English translation, which is Australia is one of the few countries that has diplomatic relations with North Korea. Okay, now it makes sense in English. Okay, but the Chinese and the English word orders are very different. And so this is a nice example of the kinds of reorderings you have to do in translations sometimes and which the system is able to do well. Okay, so how does it work? You're given one of these sentences, and the translation system has a number of rules. The translation system has a number of rules, some of which look like this. So we might bring in a rule that translates Alzo into Australia, shi into this, is, shi into is, this into North Korea, and so forth. We translate some of the words, but not others. And then the key difference between this system and the systems that came before it is we have these hierarchical rules. And these are rules that can apply to the result of using other rules. So this rule says if I see the word yu followed by anything, followed by yo, followed by anything, then that could translate into the English have something with something, and importantly, the two empty boxes get flipped, because reflecting the fact that in Chinese, prepositional phrases tend to come before the verb phrases, and in English they could go either way, but more typically afterwards. Okay, so after applying this rule, we have this partial translation. Australia have diplomatic relations with North Korea, a few countries. So now we can bring in another rule. And this rule now says this word "de" can be translated in many different ways. Why doesn't the pointer work? Okay. This word "de" can be translated in a number of ways. One of them is as an English relative clause. Okay, so if you have something, the something, that can be the something, that something, again with the order of the boxes reversed. Okay, so these rules get built up on larger and larger blocks and perform larger and larger reorderings until finally we have this partial translation. And we bring in one more rule that says this word 之一 means one of, but in Chinese it comes after the thing that it's one of. In English we put the one of before. And so this last rule will finally take that big block and swap it with 之一 and give you the desired translation. Australia is one of the few countries that have diplomatic relations with North Korea. Okay? That was kind of a compressed introduction to Hairo, but I hope that makes sense to people. Okay, so what's missing? I'm going to focus on two things that are missing. One is, even though, so it's a hierarchical system, and so you have these rules that look like they're performing reorderings and operations on what seem to be grammatical units. But really, there's actually nothing in the system that actually constrains these things to be operating on grammatical units, much less particular kinds of grammatical units. So the system would be perfectly happy to take this rule. Remember that this rule takes "de" and translates into a relative clause, and it'd be perfectly happy to apply it to those two words. And you would get the translation, the few that diplomatic relations, which is really bad. Maybe the language model would then go through and say, this is a bad translation, try something else. But as far as the basic rules of the grammar are concerned, it's just as happy to do this as what you saw it do in the previous slide, because there's no awareness of syntax in this system. Okay. There are other machine translation systems that do make use of syntax, syntax-based machine translation systems, but this is not one of them. But so if we did have some syntactic knowledge, we wouldn't do this, because this unit here, 邦交的少数, is not a meaningful or salient grammatical unit. And so it doesn't make sense to treat this as some isolated thing on which the rules should apply. So if we had the Chinese parse tree, we would never have attempted this in the first place. Okay? So syntax-based systems don't even consider this because they have this extra information, but Hairo doesn't because it's ignorant of syntax. Okay? So an idea that I tried back in 2005 but didn't work was rather than trying to do a full-blown syntax system, because that introduces complications of its own, why don't I stick to the syntax-ignorant system, Hairo, which just takes a French sentence as input and then just goes straight into the decoder. And why don't I supplement it with some parse tree information? So besides feeding the French sentence into the decoder, I'll also feed it into a syntactic parser. The parser will produce a parse tree, and that parse tree can be used as a hint for the decoder, but not as a hard constraint. Okay? So the decoder has this additional source of information which it can take or leave, and it uses it to inform its decisions. So in considering this sentence, which now has this hint here, this parse tree, it can consider applying the rule to this unit. But then there will be a feature of the model that says, well, that unit is not a subtree of the parse tree, and so a penalty is going to apply. it doesn't forbid this, but there'll be a penalty that says, well, if you can find something better, that would be better. Or, this is OK if there's some other factor that makes it really good, but as far as the syntax is concerned, this is not so good. So a penalty will apply in this case. But in this case, since the thing that the rule is applying to is a full subtree of the parse tree, then the feature would say, this is good. I'm going to let this through. Okay, so it's a soft syntactic constraint because it uses information about the tree to inform the decoding, but it doesn't force the decoding to follow the tree. It just hits. It's a soft constraint. Okay, but unfortunately, that didn't work on the Chinese English task that I tried it on. It actually worked in the submission version, and then in the final version, it stopped working. But in this past year, Yuval Martin and Philip Resnick sort of picked up on this idea and said, we haven't dug deep enough to this yet. We need to try a few more things to make sure it really doesn't work. And when they tried those further things, they found that they did get it to work. So they made the following improvements. One is instead of having a single feature that just penalizes things that violate constituents, they added the reward features that do match constituents. They added a pair of features. So there's one feature that says you get a reward if you try to translate something that matches the constituent, but then you suffer a penalty if you try to translate something that that violates a constituent boundary. And they found that using both of those features was more effective than using a single feature. So you might have depending on the task, you might have a small reward for matching a constituent, but maybe a very large penalty for crossing a constituent or whatever. This is something for the training to decide. And then they also observed that some categories are more useful than others. So there are some categories in the Chinese tree bank which are like frag or XP, and they reasoned, well, this stuff is not really that informative, but things like NP or things like S, those might be a lot more informative. So they said, why don't we try separate features for different syntactic categories? So we'll have a feature that rewards NPs, we'll have a feature that rewards VPs, we'll have a feature that rewards S's, and so forth. And the idea is that if we train them separately, then the training will be able to learn that some of these categories are more useful than others. And so the more useful ones will get higher weights. Okay? Am I making sense so far?
I don't know if you know their work that deeply, but was it related to how reliably you can bracket these categories?
That's part of it. This is going to be a bunch of factors, but one of them is definitely that the parser itself makes mistakes. So parsers are probably pretty good at NP chunking, probably pretty bad at, I don't know, identifying UCPs or something like that. So that could be part of it. Yeah. Anyway, so what they did was they set up a very large battery of experiments, and each one tried one of these more specialized features. And then they compared the results on each of these experiments and found that some sets of features worked better than others. But they only tried them basically a pair of features at a time. Because as I will talk about later, if you throw in too many features to the training method that's standardly used, then you will run into difficulties. So they ran many, many experiments. Their paper reports on probably about 50 experiments. And you get lots and lots of results. It would have been nicer to take all of these features, there's like 30-something of them. It would have been nice to throw them in all at once and let the training system just train them all at once and decide once and for all which of these features is more valuable than another. So that would have been nice, but they were unable to do this. Okay, so this is a brief summary of the training setup for the experiments in this paper, not their paper. So we're using almost 200 million words of parallel text, 2 billion words of language model text, and I'm using these tuning and test sets and this tokenizer and parser. Okay, so the baseline system, so in case that went by too fast, the test set is the Newswire and Newsgroup portions of NIST 2006. So the baseline system has 12 features, and it has a blue score of 44.6. And then we tried adding a single pair of features. So one feature said you get a reward if you match any of these constituents. And these are basically like the linguistically constituents in the tree bank. There's no frag in or UCP or X or anything like this. So you get a reward if you match one of these categories. And then there's another feature that says you get a penalty if you cross one of these categories. But if you match or cross an XP or an X or a frag, then this feature just ignores it. So this is a single pair of features, so the total number of features is 14. Okay, and this helps. So the score goes up from 44.6 up to 45. So this helps. This is nice. This is better than the original result I had back in 2005, where the syntax didn't help at all. So this is nice. Okay? But then what happens when we try what we really want to do, which is to try all of these features all at once? So you have, there's 11 categories here, so we add a pair of features for each category. OK, so here's what we really want to do. We want to add a feature if we match an NP, and a penalty if we cross an NP. A reward if we match a PP, and a penalty if we cross a PP, and so forth. So this is going to add a bunch of features to the model. It's going to bring our total up to 34. Still not a lot of features, but it turns out to be too much for minimum error rate training, or MERT for short. So the BLEU score actually is not even as good as this. So we expect to get a gain by having all of these fine-grained features so we can learn separate penalties for different categories, but it doesn't happen. The training fails. Okay? And yeah, actually, in our main development system at ISI, we've been just adding features of many different kinds, and we're up to in the neighborhood of 30, and similar experience. We're finding that we add features, but they don't help anymore. And it seems to be because, yeah, we're hitting the practical limitations of this training method. And for those of you who are not familiar with this training method, my apologies. It's called minimum error rate training. And it's basically a coordinate-wise search to try to maximize the BLEU score of a held-out data set. OK, so this talk is kind of like lots of little talks in one. That was the first one. So the second thing, what else do I think is wrong with Hyro? The first one was syntax. And syntax is something that syntax-based systems have, but Hyro doesn't. So here's something that phrase-based systems have, but Hyro doesn't. Okay, Hyro has these nice hierarchical structures, but it does not have a distortion model. So you can imagine you have this same old Chinese word again, f, de, f. In this case, the de means of. For some reason, it shines it shines everywhere except for where I actually want to point. There it goes. OK, see? F, f, de, f translates into E of E. So if you said, you know, 知非的家, then that would be the house of 知非. All right? So it's the same as English of, but the order gets flipped. Or it can translate into English apostrophe S. So 知非的家 would be 知非's house. Right? And so either of these options is possible. And the same is true even if the things to the left and the right of de are larger units. But you might imagine that translating from Chinese to English, you might have a preference for one or the other. And that preference might depend on the size of the blocks that are being reordered or not reordered. Okay. I have not checked the statistics, but you would think that this would be relatively more common. But then when you get to larger blocks, you might find a stronger preference to not reorder things. Right? Just because the larger and larger things get, then the more confusing it might get for the translator to try to swap things around. Yeah, I would have to check the actual statistics for this, but this is just it.
You know,
what?
I might guess that that's true in simultaneous translation, but there's a competing factor.
Uh-huh.
So I think the language model preference might be the other way around.
Could be. I'm sure it depends on the content of the phrases, too.
You're less likely to use apostrophe S, especially when the possessor is long. And you're less likely to use of if the... in other words, if you imagine that the...
I think that's true.
Yeah, I mean, I can go into why I think that's...
Yeah.
I would say president of Microsoft India Private Limited instead of Microsoft India Private
Yeah,
Limited.
yeah. I think that's true. I think that's true. So my point is not to prejudice the question in one way or other, but just to suggest that there could be a dependence on length. All right. So flat phrase-based systems can do this fine because there's a distortion model that says I have these phrase pairs that translate a sentence block by block, and then there's a phrase reordering model that says I can reorder the phrases, but I suffer a penalty for reordering the phrases that depends on the size of the phrase and the distance that it moves. Okay. So there's an explicit distance dependency in a phrase-based distortion model, but Hyro rules don't have any such dependency. So these rules are, the key idea behind these rules is that they can apply to very large units, and they don't care how big the units that they're applying to. They're independent of the size of those things. Okay, so this is something that is crucially missing from Hyro that a supposedly simpler system has. So how can we put this back into Hyro?
More than length, perhaps the bigger effect might be that certain lexical constituents prefer one ordering versus another.
That's certainly true.
That is certainly not there in Hiro because it's an
Right.
X.
Right, it's invisible. Yeah. So that would be another set of features that I would very much like to add. Yeah. Yes. I'm sorry? Maybe the depth of the tree. Yeah, that could be hard for the decoder, but yeah, definitely. Okay, so for now I'm concentrating on size. Okay, so I need the model to learn a dependency between whether or not reordering occurs in a rule, so reordered versus not reordered, and the size of the things being reordered. Okay, so I have one variable that says reordered or not reordered, and then I have another variable that tells me what the size of the things being reordered are. And I need to learn a dependency between these two variables. Okay, so one way to do this would be to go through my training data and try to learn a probability distribution of P of reordered given size. And so when you do this, in fact, you find that the probability of reordering is relatively much higher for size 1, 2, 3, and then it goes down exponentially. And then when you're dealing with size 10 or 12, then the probability of reordering becomes very low. So we could build a generative model like this and then add it in as a single new feature of our model and then rerun our minimum area training and see if that helps. Okay? But it might be more interesting if we did something, again, more fine-grained. Because maybe the probability of reordering in our training data is, maybe our training data reorders things more aggressively than we actually want our system to do, because maybe we want our translation system to produce more literal translations than the training data. Or maybe the statistics that we collect from the training data are not necessarily that accurate. So it seems nicer to train this model directly in the context of the translation task. If it performs a reordering that's bad, then you want the system to directly respond to the negative effect of that reordering. So we could do that. We could do that better if we had separate features for various pairs. So we have a feature for reordering of a block of size 1. And we have a feature for not reordering a block of size 1. And we have a feature for reordering a size of block 2, and so forth. And for good measure, we might throw in another feature that says, in general, this feature fires whenever I perform a reordering, and this feature fires whenever I don't have a reordering. So the star is a wild card. All right? So again, this is the same baseline as before. And when we add in the single new feature, that's probability of reordered given size, that helps. That's pretty good. It goes up by 1.2. But then when I add in lots of small features, then the performance goes back down again. Same story as before. Okay? So stuff that we thought might help, well, so this helps. But then stuff that we thought would be even better actually is worse. Okay, so what's the problem? The problem is this minimum error rate training that I keep talking about. Practically speaking, everyone knows it's limited the number of features. When I ask around, people disagree about what that upper limit is. Some people say 15, 20, 25, 30, but it's always in that neighborhood. Nobody runs MERT on 50 features. And there's been a lot of work in the literature on trying to replace MERT with some kind of better learning method. So these are a few of the more well-known papers. I should have added Zhifei's AMTA paper. So Percy Liang applied perceptron to the problem. Tillman and Zhang used stochastic gradient descent. And Watanabe et al. 2007 used an online algorithm called Mira. There's also this very interesting paper by David Smith and Jason Eisner at ACL 2006 using LBFGS and deterministic annealing. And their objective function was an expected blue score. And it seems like this method should work pretty well on lots of features. But this is a question for you.
No, we just compared it more on
Right.
the same set.
And the comparison was favorable.
10 features, I think,
Yeah.
that Mark was using. So you're right that the method should be fine. And we have done this kind of annealing thing in other contexts.
Yeah.
One thing to say is that the expected blue, as you cool the temperature, turns into optimizing the actual blue.
Right. But for any finite temperature, you have a gradient, and so you can apply this method. Yeah, so it seems like worth trying. I think I'd probably want to.
Yeah, no, you should.
I'll probably do it real soon. Yeah.
It should be a standard technique, and everybody toolbox because it's very easy to do.
Yeah, yeah. But OK, good. Thanks for answering my question. OK, so what are the technical obstacles to replacing MERT with another learning method? I think one of the largest problems is the sheer scale of the systems that we deal with. So up above is a typical setup for like the kinds of systems that people enter into the NIST evaluations or Gale evaluations. You have a set of training data that you get your phrase table or your grammar from. This is just not working. You shake it a little bit?
Batteries are losing. I don't know why.
Is it like mechanically powered? Oh, now it's always on. Wonderful. OK. So we have this training data, typically like 150 to 250 million words. This is parallel text. And we get our grammar from it. And we also get various, actually, I should watch out not to blind anyone now. This is kind of dangerous. And we get our phrase table or our grammar with various probabilities associated with it. And then there'll be a much larger monolingual corpus. These days, they're pushing 2 billion or more words. And a language model will be trained from this monolingual corpus. And then those models, generative models that were learned from those data, will be fed into MERT as features of the model. And these systems are very, very large. So decoding sentences is computationally pretty expensive. Even a fast system will do 10 sentences per second. A system like the ones we use at ISI are more like 10 minutes per sentence. And so we can't practically run MERT on a large amount of data because MERT involves decoding your tuning data repeatedly. And if your decoder is slow, even 10 sentences a second, then you can't go running this on 200 million words of parallel text. Or maybe you can, but certainly at ISI we can't. So there was this work by Tillman and Chiang, which was very ambitious, and they wanted to go for the purely discriminative approach. And they said, we don't want any generative models whatsoever. We're just going to take our parallel text. We're going to extract phrases from it, and then we're going to do all of our training on the exact same set of data. It was very ambitious. They got up to 7 million words. The performance was not very good. It's hard to imagine this scaling up to data sizes that big, especially since we don't even have 2 billion words of parallel text. OK, so some other approaches that have been tried. This was Percy Lang's work at Berkeley. Here, you have a setup that kind of resembles more the standard setup. You have a separate training set for getting your grammar and your language model, and you have a separate set for doing your parameter estimation. But still, they tried to make this pretty big, 700,000 words. And their decoder was pretty simple. It didn't have reordering as a phrase-based system. And so they were able to run on 700,000 words. So this is starting to get more practical, because at least you can train your language model and your phrase table separately and stuff like this. It's not as theoretically pure, but it's more practically scalable. And then last year, Watanabe et al. Did an experiment with a setup that basically is identical to what people standardly use in the largest systems. They used a very large parallel text, a very large language model, but then they replaced MERT with a different algorithm called Mira, running on a pretty small amount of data, 20,000 words. Okay? And the interesting thing about that paper was they were able to show that they could learn quite a few features, even from quite a small amount of data. One downside was they had to decode it 80 times, which is kind of a lot. Usually we run MERT 8 to 10 times, and so 80 times is kind of a lot. But this was very interesting work. And so this is the work that we're building on in the present work. We're using Mira, and we're trying to use a full-sized setup of training data. Okay? And we're making some improvements. The two main improvements, there's a few here and there, but the two main ones are, one, we're trying to use more of the forest, the parse forest, the packed forest, to get more stable and better learning. And the second difference between our method and Watanabe's is it's parallelized. In our experiments, we use 20 processors, and that speeds it up by about a factor of 20. And so both of these are geared towards making the method even more practical. So instead of having to decode my tuning set 80 times on a single processor, I can decode it to 10 times on 20 processors. So it's much, much faster. And our findings, we're able to show that even when you don't add any features, even when you use the same features, the performance is as good or sometimes even a little bit better than Mertz, and the speed is also as good or maybe even a little bit better than Mertz. But what we're really interested in is being able to add more features and getting improvements in translation quality. How many more features did we add? We've been pretty modest so far. We've made it up to 56 features, which is a lot more than Mert can handle, but still a lot less than what people really want to get out of methods of this type. So we're getting there. But so far we've scaled to 56 features.
So when you say it's as good as Mert, it's not better.
On some tests it was better, on some tests it's about the same. Yeah. And never significantly better. Oh, that's not true. No, on one test it was significantly better. But there might have been, yeah, I can talk to you about that later. Yeah, I didn't know that there weren't that many tests. There weren't that many. OK, so here's how the mirror algorithm works in a nutshell. And if you want more details, you can refer to the paper. So it's an online learning method. So we translate a sentence, and then we try to learn from each sentence as we process it. Okay, so we choose a training example, and we decode it to get a set of hypotheses E sub j. We choose one of them to be like the gold translation. We pretend that that's the correct translation. We call that E star. Then we calculate the loss of each of the EJ. So this is how much worse is each EJ than E star. And then we perform an update on the weight vector W. Okay, and the update is the minimizer of this objective function. This part of the objective function says, I want the new weight vector to be close to the old weight vector. It would be kind of crazy to make the weight vector jump all over the place. I want to be conservative. This part of the objective function says, for each of the EJ, I want the model's idea of the difference between E star and EJ to be at least as big as the real difference between E star and EJ. Okay, does that make sense? So this is called the margin, and the model is h dot w, h of e dot w. So this whole term is the model's idea of the difference between E star and EJ, and LJ is the real difference between E star and EJ. Yes?
J is the size of the hypergraph or just the translation?
I'm being agnostic about that so far. It's just some set of candidate translations. Yeah, and no, right now it's not the entire hypergraph.
Just like this.
There's typically about 30 examples in there, but I'll talk later about how to select them. Okay, so graphically, will this reach? No. So graphically, what's going on? So this is a scatter plot. The x-axis is the model score. So this is how good the model thinks each translation is. And the y-axis is the blue score. This is how good we pretend that this is objectively how good the translation actually is, the y-axis. Okay? So ideally, we want all the dots to be lined up along a diagonal like that. Right? But of course, they're not going to be. Suppose these are our EJ. These are our candidate translations. We select that one at the very top to be E star. And then the vertical distance between a point and E star is its loss. That's the blue difference. And the horizontal difference is the margin. That's the model's idea of the difference between the two. Okay? And the constraint says I want the margin to be bigger than the loss. In other words, I want everything to be in the upper left diagonal slice. Because yeah, stuff down here is bad because these are translations that are bad, but the model thinks they're good. We want to eliminate those, right? And we want to move that guy, which is the gold one, as far to the right as possible. So we want everything to move into that upper diagonal. So an update might do something like that. But because of this first term, the 1/2 w prime minus w squared, it might not satisfy the constraint perfectly because it might. If you have to make too drastic a change to the weight vector to make that happen, then it'll just do its best. So you have these two objectives that it tries to satisfy simultaneously. Okay, does that make sense? So there's the objective function again. And for the solution, you can see the paper. But in general, it has a form very similar to the perceptron update. Basically, we're going to be adding the feature vector of the gold translation and subtracting the feature vectors of the other translations. And they're all weighted by these values alpha. And that's the problem is to determine those alpha.
David, it
Yes.
looks like even if the best hypothesis among the J is the best according to your model, this will still monkey around with the
Yes.
model because
Yes, thank you.
the others, they're worse than the model thinks they are.
Right.
And so you still tweak.
Right. So the idea is that even if you're getting perfect translations, that's not good enough. You want to make sure that everyone else is really far behind. And if there are any really bad translations that were like tempting, even if it didn't select it, if there were any really bad translations that were tempting, the model will try to push them down. So hopefully this will increase its generalization ability to new data. You can't just get the right answer by a hair. You want it to be safe. Okay, thanks. Okay, so there's these translations E star and the EJ. Okay, and selecting both of these is tricky when applying to the translation problem. So first we'll talk about E star. E star normally, if you're doing like a classification problem, you're trying to classify images as digits, then E star will be the digits 0 through 9. It'll be the correct answer. In the case of translation, there's no one correct answer. And so this is a nuisance when trying to apply a lot of machine learning methods to MT because we actually don't have the correct answers. So we have to kind of do our best. And various methods have been proposed for choosing this E star. Probably the two of the more well-known ones are called local updating and max blue updating. So actually, I'll talk about max blue updating first. It's the more intuitive one. Max blue updating is we look at the space of all the translations we could get, and we choose the one with the very highest blue score. Okay, so you imagine a whole cloud of translations. I didn't show the whole cloud, but this guy is the max blue translation. It has a blue score of 95. Wouldn't it be great to have a blue score of 95? And it's sitting there in the space. What's wrong with max blue? The problem is that the model thinks that all the good translations are out here, and the max blue translation is way, way, way to the left. Why? Maybe we had to use some really weird rules to get the translation just right. Or maybe if there's any overlap between our training data and the tuning data, then there could be just some rule that was just gotten from that one sentence or something like that. Anyway, there's something about this translation that makes it coincidentally, you could say, have a translation that's very close to the human translation, but there's something really weird about it, like it uses some really rare rules or something like that. What happens in practice is if we try to update towards that point over there, we try to crank this point to the right, and we try to move these guys to the left, well, the model will end up flying all over the place, and the search will be very, very unstable. And this has been observed by Percy Liang et al., and also by a paper by Abhishek Arun and Philip Kuhn, where they compared these various methods. So we need to do something more conservative. It's too aggressive to try to go for the very, very highest blue score. So there's another method called local updating. And in local updating, we choose an n best list. Here, n's equal to 10. We choose the 10 best list. And because they're the best translations according to the model, they're all hanging out here at the right end of the graph. And we choose the highest blue score from those 10. OK, this is local updating. So this is a lot more conservative. This point is, we're not going to get crazy updates this way. But still, it's a good blue score. 78 is a really good blue score on this data set. OK, so but what objections might we have to local updating? The main one that I have is that we're using the n best list, and we're relying on the fact that the n best list is short. If n is too high, then this n best list will end up including that guy. If n is too high, then local updating reduces to max blue updating, and we have the same problem as before. So we have to choose this n very carefully. Too low, and the blue scores won't be good enough. Too high, and it could go unstable. And what's worse, this value of n could depend on properties of our decoder. And it could depend on the length of the sentence. So for very short sentences, if we take like 100 best list, it could actually be a pretty good sample of the whole forest. But for a 100-word sentence, it'll just be a tiny little tip of the iceberg. So the n best list is actually not a very good way of sampling the top part of the forest, because the forest can be radically different sizes depending on the sentence. So it's kind of tricky to figure out what the right value for n should be. All right, so what are we going to do instead? We're going to choose the E star as the optimizer of this objective function. So what is this objective function? This first term says, I want E star to have a high blue score. This second part of the objective function is the part of the mirror objective function that depends on E star. So basically what this is saying is, I want E star to be the highest blue translation, but I'm willing to choose a lower blue translation if that means it'll be easier to optimize the mirror objective function. Okay, so basically this is saying, yeah, I want a high blue translation, but I also want to make life easier for myself. Okay, so then this mu adjusts how willing am I to go for a lesser translation if that means optimizing the objective function will be easier. So I set mu equals 0.5, and that reduces to this, which might be a little more intuitive. That just says I want to choose the E star that has a high blue score and has a high model score. So graphically, that looks like this. This is my 10 best list. That's the point that local updating would select. And that mu equals 0.5 point is the Oracle translation that our method would select. So it has a higher blue score. It's like upper 80s or something like that. But it's not way in no man's land like the max blue translation is. It's still not too far. Okay, so maybe or maybe not, this will give better results than local updating. But notice there's no longer any weird dependence on the length of the sentence or any properties of the decoder or something. It's all defined in terms of the blue score and the model. So I don't know. I feel a little more comfortable about this than using the n-best list. Okay, does that make sense? All right, now how do we select the EJ? And the EJs that are different from E star are the ones that are used as the negative examples. The E star is used as the positive example. The other EJ are used as the negative example. In the perceptron algorithm, there's only one EJ. It's just the one that the model guesses. In Mira, it can be whatever you want. There's lots of variations of Mira, and so we're free to choose one of them. So what Watanabe do is they choose the n-best list. And if they make multiple passes through the training data, then they will accumulate the n-best list. And they use those as their negative examples. In the approach of Taskar et al. In a series of papers, maximum margin Markov networks, max margin parsing, and so forth, they advocate using the entire forest. So you use the actual whole space of all translations as negative examples. It's always better to use more information. Why not use all of it? And that's a very nice approach. But they have a formal requirement that you be able to calculate the loss function for every single translation in the forest. And the forest has an exponential number of translations. So the only way to do this efficiently is if the loss function decomposes somehow into the hyper edges of the forest. And in the case of blue, we can't do this, at least not exactly. So what I'm trying to do is the next best thing. This is the objective function. If you remember, basically, this objective function is going to try to minimize the max of this. So if we include the max of this, then that might be almost as good as covering the whole forest. Okay? So the whole forest has points everywhere. But the ones that Mira will target are the ones that are to the most to the lower right. These are the most dangerous translations. They're the ones that are low blue, but the model likes them. Okay? So if I search through the forest for just to find the handful of translations that are the furthest down on this frontier, then if I include these as my negative examples, then hopefully that'll be almost as good as if I had included everything. That's the hope. Okay, so this graph shows my EJ. Except for those three guys at the top, those are the max blue translations. There's 30 translations here, and I use those as my EJ. But it's especially these that I think are going to be used by the learning method. Okay, does that make sense? Okay, how do we actually do this? We're given a forest, and we have to try to pluck the max blue or the max loss translations out of the forest. And we have to do this approximately. And the method that I'm using is really similar to Marcus Dreyer's method from 2007. There are other ways of doing it. So there's more work that's been done here by Roy Trumbull using a linear approximation to blue that is decomposable into the hyperedges of the forest. That would be really interesting to try also. And the fact that blue is not decomposable in this way is annoying for many reasons, both algorithmic and evaluation related. And if you're interested in that question, you can see another paper that we're presenting at UMNLP. Okay, so the other improvement that I mentioned that we're making to Mira is parallelization. And parallelizing MERT is pretty easy. You just decode sentences on lots of parallel processors, and then the actual feature tuning involves random restarts, so you do random restarts on different processors. So that's really easy. Parallelizing Mira is a little bit harder, because we decode a sentence, and then we make an update to the weight vector, and then we decode a sentence, and we make the weight vector. The weight vector is constantly changing, and so we have to do a little more communication between the nodes to make this all go. Okay, so the scheme that we use is pretty simple, and it seems a little scary at first, but it turns out to work all right. Basically, you just run Mira on 20 processors in parallel, and every time one of them obtains a set of translations, a set EJ, it sends them to all the other nodes in the batch. And then whenever a processor is finished decoding, it will use the EJ that it obtained from the decode and any other EJs that have been waiting for it, and it uses all of those together to update the feature weights. So the approximation is that the translations it received from the other nodes were obtained using somebody else's weight vector. So they're not optimal, but they still have useful information. So we still use it, and it turns out to help. Okay, so we've run this on 20 processors, and it works fine. OK, so now I'll present the experimental results. Basically, you've seen this slide before. The only thing I'm adding here is that normally, for both of these methods, we have to decide when to stop training. For MERT, the standard practice is just to stop training when the blue score stops increasing on the tuning set. For Mira, the criterion we're using is to use some held out data and to stop when the score stops increasing on that data set. And it turns out that it makes at most like a 0.2 blue difference. We probably could have just done the same thing that we do with MERT and stopped when the score stopped going up on the tune set. So these are the numbers that you've seen before. With MERT, we start at 44.6. Syntax helps, but using the fine-grained syntax features doesn't help as much. And using the distortion model helps, but using the more fine-grained distortion model doesn't help as much. So when we run Mira on the same 12 features, actually we get a higher score on this test set than we did with MERT, and that's significantly better. Part of the reason for this is that the Mira translations tend to be slightly longer, and there might be some length-related issues because of the different genres involved. So I don't place too much stock in the difference between these two. It's statistically significant, but I wouldn't go around saying that on the same features, MERT is significantly better. We'd probably have to go and do a subjective evaluation.
So you don't want to claim that the Mira baseline is better because it's not just that you're trying to pull the best translation up, you're trying to suppress the others. The translation is different.
Yes.
Maybe Mira training generalizes that. Because after all,
that's possible. Yeah. Right. So if you look at the paper, you'll see a breakdown by genre. And what happens is that for this line versus the MERT line, the newswire score goes down a little bit. The web score goes up quite a bit. So maybe it's because of generalization, or maybe it's just because the Mira translations are longer. I don't want to make any strong claims, but I would like for what you said to be true. Yeah, that would be cool. All right, so when we run Mira on the fine-grained syntax features, 34 features, the score is 46.4. Okay, so this line gets compared with the syntax fine line up there.
What about you just go to 14 features?
I'm sorry?
What about you just go to 14 features instead of 13?
I'm sorry, I didn't run that. Yeah, you've all told me to run it, and I didn't. Yeah, sorry. Okay, but this is definitely an improvement over the 45. What?
GFA is hoping it'll be even better than 46.4.
Oh, I see. I should run it. Yeah, but it's not in the paper. Yeah, thanks. OK, and we do the same thing for the distortion features. The blue score goes up to 46.7, so this is looking pretty good. And of course, the last question is what? What happens when I combine them all together? Then blue score goes up to 47.2, training on 56 features. OK, so this looks like it's doing pretty well on this feature set.
So do you think this will have some sort of recognition, but the MERT doesn't have any recognition?
So we talked about this before, and there's no explicit regularization term. I am doing averaging, so it is averaged Mira. And maybe there's something in the method that does some kind of implicit regularization, but there's no explicit regularization term. So I don't know. Mirth, there's no regularization at all.
And
Yeah.
we don't do average.
That's right. I'm not sure what it would mean to do averaging. Oh, to average all the iterations? Yeah, that would be interesting, actually. No, nobody does that. Any more questions? Okay, so some more results testing the improvements that we made. So this has to do with the methods for selecting the oracle translation and the negative examples. Okay, so this chart's a little bit weird. So here's the number I just showed you. I'm sorry, it's the system that I just showed you, but this is on the dev set now. So this is the mirror system as I've described it so far, 53.6. We can compare it against local updating, and we lose half a blue point. So local updating is we just take the 10 best list and select the highest blue score from the 10 best list. So it makes a half a point difference. It's not that big, but it's there. So what happens when we take local updating, but we add those negative examples? And it turns out not to help. So it seems like we're not gaining anything by adding those negative examples. Okay? But what happens when we take local updating and we take local updating, but switch to the new method of searching for the oracle translation, the more aggressive oracle translation? And I wrote fail here because the blue score is just horrible. The translations get longer and longer and longer, and the method can't figure out a way of getting them back shorter again. And I killed it. Presumably, it would just keep getting longer and longer. It's really nasty. So my interpretation of this is that these negative examples are serving as kind of a counterbalance to these more aggressive oracle translations. They're stabilizing the search so that we can use this more aggressive oracle translation. And so we end up with a net gain. Does that make sense?
So what about the next blue update?
Oh, it would be a fail. I haven't actually run it, but I mean, I run it for like a little bit, and yeah, it looks bad. Yeah, because this is already much more conservative than Max Blue. Right, Max Blue would be just the best blue, and here I'm mixing the model, so this is more conservative than Max Blue, and already it failed. Yeah. In earlier experiments, I tried doing like model plus, a quarter of blue, and that worked okay, but a model plus 1 times blue is not good.
What about just randomly sampling?
Oh, that's a really good idea. Yeah, the code's in there. I should just try it. Yeah, but so the hope is choosing those negative examples is kind of the frontier, and that's what the update will go after anyway. Those are the ones that get subtracted out. So my guess is that random sampling won't make too much difference, but it's worth trying. It's worth trying. Any more questions? Okay, so testing the parallelization method, one of the reviewers suggested, why don't you do the same thing, but just run the parallel processors completely independently and then average their weight vectors together. So they don't communicate with each other at all. So I said, okay, I'll try it. And it makes half a blue point difference. So sharing improves the score by half a point. If we don't do sharing, it's worse. And it seems to be slower, too. So that's not too surprising. Number of iterations. Oh, the communication overhead's nothing compared to the slowness of my decoder. Yeah. What?
With parallelization, are you worried about replicability because of the
Yeah.
type of the messages?
Yeah.
So basically, you can broadcast something, but I might not get it or incorporate it.
Yeah.
I mean,
Yeah, there's a lot of randomness involved.
Yeah,
yeah.
right. Actually, it's not just the network latency. It's also I might be slower on one example.
Yeah.
Slower, making a slower pass through the training set.
Yeah.
On this,
It makes it very irritating for debugging. Yeah. On the other hand, randomness is kind of good. So actually, when I select the sentences, I don't go in order to the test set. I randomly shuffle them, and that actually turned out to stabilize things quite a bit. So then, in that sense, randomness might be a good thing. What's that? Oh, yeah. Sorry. Yeah.
I mean, there is a way to sort of, if debugging or reproducibility was an issue, you could have something like a block synchronous thing where you start 20, each of them does a sentence.
Yeah. Or you could run it on a single processor,
Right.
but that would just take too long. Yeah.
No, to see the
Yeah.
effect of this business with
I see.
updating with someone else's W.
Yes.
So you could
Yes.
simulate that, but in
Yeah.
a predictable way.
Yeah. 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 In fact, that was one of the first things we did. We did a simulation. One of our summer interns, Michael Bloodgood, he did a simulation using Perceptron and basically just said, always update like 3 steps later or something like that. And yeah. Okay. Any more questions? All right, so this is just my summary of conclusions. Mira works. We already knew that from Watanabe 2007, but we've made a couple of improvements. Using more of the forest is better, and that's a good thing. In local updating, yeah, one property that I found unappealing is that the more of the forest you use, the worse it could potentially get. But here, apparently, using more of the forest is better. And parallelization works. And these features that we've talked about are interesting in their own right. Soft syntactic constraints help Hyro, which is not a syntactic system, and they help more if we use lots of them. And there's this structural distortion feature, and those help. And that was kind of a gaping hole in Hyro, which is now closed. OK? Thank you very much. Yes. Oh, good.
So what about the effects of the size of the dev set? So,
Very important question.
yeah, what would be the implications of if you could scale to decoding your entire training set? And would you think that would result in?
So it would be improved in the sense that we'd have the capacity to learn more features if we have a larger dev set. What's not clear at this point is what's the relationship between the dev set size and the feature set size. So both the Liang et al. Paper and the Watanabe et al. Paper trained on many more features than I'm training here. And it was especially confusing to a lot of people with the Watanabe paper because they had a very small training data, half the size of this one, 663 sentences. And they were able to learn, I think, hundreds of thousands of features from that very small data set. And a lot of people said, how is this possible? And it would be good for future work to do a more thorough investigation of that relationship. Yeah.
Let me interject by speculating that the Mira objective function is sufficiently different from what people typically do, for example, with the perceptron or with numeric training, that think of it this way, that even though you might have only 600 sentences, you're looking at a large, I don't know how deep n was, but if n was 100, you're looking at a fair number of examples which go into that max.
Yes.
Max over J.
Yeah.
So you're looking at all sorts of, because one of the problems with a 10,000 or 1,000 sentence set for training the model is that if there are particular features which help one or two sentences, then they might get a lot of weight.
Yes.
But if at the same time they help something further down in the best list in that sentence,
yes,
luckily you happen to put
a
good one first.
That's true. So there's more information being brought to bear.
So my speculation is, speculation at this point, is that Mira won't need as much more data as features grow. Basically, you're computing expected loss instead of
Maybe. So, I mean, obviously, one item for future work is to start throwing in lexicalized features and to start testing this. And yeah, it would be nice to try to observe that relationship.
So are you saying the perceptron have this under-training problem of all these features, but Mira doesn't have this problem because the objective function here is undetected?
So here's an example of what Sanjeev is saying. If you start with an initial feature weight where the output translations are shorter than the reference translations, what the perceptron will try to do initially is it will try to decrease the language model weight, because language model weight always says longer sentences are less probable than shorter sentences. So if it sees the reference sentences are longer, it'll say, the language model must be the problem. Let's downweight the language model. And of course, it'll also downweight the word penalty. Yeah, it'll downweight the word penalty. It'll downweight them together, and it'll do this and do this. And very frequently, the language model weight will go negative. And it won't be until after it goes negative that it'll start to figure out, maybe this wasn't such a good idea, and then it'll start to separate them and say, okay, the language model needs to have a high weight, word penalty needs to have a large negative weight. Whereas when you include the negative examples, the one in the lower right corner of the graph, then pretty much right out of the bat it says upweight the language model, downweight the word penalty. So that was something qualitative that was very nice to see.
So even with the 12 features, we could see what we are doing differently.
Yeah. Yes?
You mentioned 80 iterations. How long did they take?
Oh, I'm sorry. On average, on the runs I did, it was like 10 iterations.
Oh, 10.
10 passes through the training data.
I remember seeing 80 something.
80 was for Watanabe et al.'s method. Yeah. And I'm not sure if they meant that converged after 80 or if they ran it for 80 and then looked for some kind of max point within the 80. They didn't specify.
Because in the dev set
I typically ran for 20, and then I looked for the best point, and the average of that best point was like 10 iterations. Yeah, and I followed the same procedure for MERD, and it was like, no, I'm sorry, 8 for Mira, and it was like 9 point something for MERD. Yeah, so they're very close to each other. Yeah. Yes.
So given that Blue has some undesirable features for your setup, and given that Blue is just some arbitrary objective function, and we could define some other, what would you look for in an objective function to make it most desirable for this setup?
So I actually prepared a whole bonus talk to answer this question, but I know I don't have time for it. But I just want to show you the title slide. So the key property that I would look for in a metric is decomposability. So the score of a document should decompose into a weighted average of the scores on the sentences. And there are several like really absurd, disturbing examples in this paper that show why this is a really important thing. And it's not too much to ask. So TER does this. But then for the purposes of this online training, we would want further to be able to decompose down to the hyperedges of a parse forest or a phrase-based translation lattice.
So the immediate thing that prevents Blue from decomposing is the brevity penalty?
Everything, yeah. Yeah, but already just whenever you use precision, then already you don't have this property. Because precision lets you choose which sentences you'll be scored more heavily on. Yeah, so WER has all of these properties. You can calculate it all the way down to the hyperedges of the lattice. And in this paper, which does not have this title, my co-authors would get mad at me, we proposed a metric called foreground recognition rate, 4GR, and that's a cross between WER and Blue. And that also is, you can calculate it all the way down to the hyperedges. So it would be interesting to combine 4GR or Roy's linear approximation to Blue with a method like Taskar et al.'s max margin parsing to do training on the whole forest all at once. That would be really cool. That's what I hope to try next. But yeah, in the meantime, we're stuck with Blue, so we have to make lots of approximations, which I've glossed over. Yeah.
I remember in the slide before your parallelization slide, I think there was some question on that.
Before the description of parallelization?
Yeah. That's the slide. I don't know.
Plus or minus 1?
Not that. Not that. Okay, sorry.
Okay.
I think you just made a statement that you had a question and you can't remember that, but someone was.
Yes.
All right, thanks, David.
All right, thank you.